Is to try and identify the best fuels and operative conditions that allow the formation of pollutants to be minimized. And in this context, alternative liquid fuels gained a lot of popularity because ALS droplet from the atomization process. The light component in these droplets would evaporate immediately and burn in the homogeneous combustion region, while the heavy component accumulate inside the droplet and lead to the formation of solid residuals that burn as well. And of course, this is terrible for the environment and for the combustion efficiency itself. But the problem is that, as you can see, the spray combustion is a complex and chaotic phenomenon, so we decided for this work to focus on a simplified configuration, which is an isolated droplet. By doing so, we can neglect the interactions between the different droplets that compose the spray. We can refine our understanding of the evaporation and combustion of isolated droplets, and finally we can also develop subgrid scale correlations for engineering models like for the Euler-Lagrange model for spray combustion. The problem of isolated droplet has been studied probably since the 50s, but probably even earlier, and starting from the famous D-square law, that it was based on a lot of assumptions that were successively relaxed by different authors, except from the main assumption of this model, which is that the droplet is perfectly spherical, and also the gas phase environment is spherical as well. And this assumption allowed complex multi-dimensional system of equation to be reduced to a 1D system of equation that can be solved in an efficient manner, and including complex kinetics, radiation, and diffusion modeling. The problem is that if you observe a liquid droplet carefully, you see that actually droplet deformation, surface tension effect play a major role in the dynamics of this system. This is myself at the Exploratorium in San Francisco. It's a great museum. If you pass by there, you should go. And so instead of using a spherically symmetric model, we decided to go for interface resolved simulations, which are multidimensional fluid dynamics models that are able to directly account for droplet deformation, buoyancy-driven flows, liquid recirculation effects, but also, why not, turbulent condition and interactions between different droplets. Of course, these models have drawbacks. They are computationally expensive and they require advancing the numerical solution strategies. But using this model, we can move toward the direct simulation of a full spray combustion problem. So, in this presentation, I will talk to you about how can we resolve multi-component evaporation and combustion in interface resolved simulations. I will briefly show you the mathematical equation and then how we resolve these mathematical equations, so the numerical discretization strategies, and a brief validation of the numerical discretization, and then show application to two specific problems, which are droplet evaporation and droplet combustion, with comparison with experimental data. And then we will draw the conclusions from this work. Okay, so the mathematical model is made of a set of conservation laws on mass, momentum, chemical species, and mass fraction, under the main hypothesis that the thermodynamic pressure of the system is constant. So the density changes are just a function of temperature and mass fraction gradients. We resolve the momentum equation for the velocity, the chemical species equation for the mass fractions omega, and the enthalpy equation in temperature form. The black terms in this equation are the incompressible model. We extended it with a variable material properties formulation, the blue terms, including variable thermodynamic and transport properties, while the red terms account for the chemical reactions. These equations are valid just in the bulk phase, in bulk liquid and in the bulk gas phase, but not across the interface. Across the interface, we have to integrate the mass momentum balances in order to obtain a set of jump conditions, so a set of essentially interface, gas-liquid interface boundary conditions, which connect the two phases. In particular, you can see that we have a velocity jump, which is a function of the vaporization rate m dot, and the density contrast between the liquid and the gas phase. This is typical of a phase change simulation, of course. The pressure jump is a function of the surface tension and the recoil pressure, which is actually negligible most of the times in these systems. We have continuity of mass, species, enthalpy. And this set of equation of jump condition is closed assuming a vapor-liquid equilibrium at the interface, which translates into the continuity of fugacity and temperature across the interface. Okay, so let's see how we resolve this set of equations, starting from the core of each multi-phase model, which is the representation of the gas-liquid interface. So in this, there are different methods that were proposed in the literature to describe a gas-liquid system. Volume of fluid, level set, front tracking, there is still development in this method. But we decided in this work to use the volume of fluid model because among these ones is the one that is mass conservative by design, let's say. So when we deal with chemical reactions, chemical species, and combustion, mass conservation is a major concern, so we decided to go for the volume of fluid model. How does it work? Very briefly, we introduce an indicator function h, which varies sharply at the gas-liquid interface. It's equal to 1 in the liquid, 0 in the gas phase. We divide our domain in a number of cells where we discretize the indicator function as a volume fraction. And so if we transport the volume fraction, we can effectively transport the gas-liquid interface. How do we do that? We need to do it in a sharp and conservative manner. So first of all, we approximate the position of the interface in each interfacial cell as a line, as a plane in 3 dimensions. And then using the dimensional split procedure as described by Weymouth-EU, we calculate the liquid fluxes across the faces of the cell as the intersection between the total fluid fluxing in the downstream cell and the planar interface. Using this method, we can transport the interface in a sharp manner, and it's volume conserving up to machine accuracy for incompressible flows. In this case, in my presentation, not all simulations are incompressible. If the flow is not incompressible, this method is still mass conserving because volume changes, volume variation compensate the density changes. So the message here is that if we have an interface velocity, we can transport the interface, right? The interface velocity with phase change depends on the liquid velocity, so a divergent-free liquid velocity for incompressible flows, and a phase change velocity, which is a function of the vaporization rate m dot. The problem is that the vaporization rate is computed at the cell center of the interfacial cells, while the phase change velocity and the interface velocity must be computed at the cell faces. So we introduce an appropriate methodology to interpolate the phase change velocity from the cell center to the cell faces using an upwind interpolation for all those faces in contact with a single interfacial cell, and a linear interpolation for those faces which are in contact with 2 interfacial cells. In this way, we can get a pure volume of fluid approach which does not require expensive extrapolation of the vaporization rate. We can avoid under and overshoots, which are typical of those methods that account for the phase change velocity as an explicit source term. We may have a drawback when we have small droplets, but that is not, does not affect the results in these simulations. So now the problem is how can we calculate the liquid velocity? And the liquid velocity is computed from the Navier-Stokes equation resolved in the one-field formulation, a classical one-field formulation that was extended, introducing the volume expansion term in the continuity equation. However, you can see that if we resolve the Navier-Stokes equation in this way, we can retrieve the information about the Stefan flow, which is the radially outward velocity profile given by the strong density jump between the liquid and the gas phase in the phase change. but the droplet is transported in a completely non-physical manner. It's completely deformed by this velocity field. And this happens because in the one-field formulation, the velocity at the interfacial cell is an average between the liquid and the gas phase velocity. And this is fine if we have a continuous velocity field. But if we have a discontinuity, the liquid and the gas phase velocity may vary by order of magnitude. And so if we just assume that this is the liquid velocity, we have a strong error in the calculation, in the transport of the interface. So to overcome this problem, we decided to propose the so-called double pressure velocity coupling. So essentially we resolve another set of one-field Navier-Stokes equation, which is identical to the previous one, but where the volume expansion is equal to 0. So it's like an incompressible flow problem. And from this set of equations, we obtain a velocity that we use to approximate the liquid phase velocity. In this way, you can see that we maintain the information about the Stefan flow around the droplet, but we can also consume the droplet in a physical and conservative manner. So this velocity is used just for interface advection and for the liquid phase. The droplet shrinks due to the phase change, but the only problem is that we are decoupling the information about the Stefan flow, so the phase change velocity, from the velocity of the liquid phase. So we also implemented an additional method which was proposed actually by Tanguy in 2006. It's based on the Gauss fluid method. This is the radial profile of a velocity field for a microgravity droplet. You can see that we have the liquid velocity, the gas phase velocity, and the jump at the interface, right? So the Gauss fluid method tells you that you can construct a prolongation of the liquid velocity in the gas phase domain and of the gas velocity in the liquid phase domain. And in this way, you can create two velocities which are continuous and eventually divergence-free at the interface. So this method, it's actually more complex. It's the same proposed by this paper. It requires additional projection step for the accurate transport of the liquid velocity. But it's nice because it does not necessitate a localized source term in the projection step that may lead to oscillations in the velocity field. The only problem is that it has worse mass conservation because we are directly modifying the continuity equation in this method. The scalar field transport equation, omega is the mass fraction, but also the temperature follow the same principle, are resolved using a two-field approach, meaning that for a single scalar field omega, we resolve one equation for the liquid phase and another one for the gas phase. And we separate each operator in order to discretize them accurately. In particular, the advection step is performed using the same geometric fluxes procedure used for the volume of fluid transport equation. The diffusion step is resolved by considering the phase fraction, so the amount of phase of the cell occupied by the phase being solved, while the chemical reactions are resolved by coupling both species and temperature in every cell in a stiff OD system of equation. This is necessary because the chemical reactions are not just a source term that you compute in your equation, because if you calculate this term in an explicit manner, you would need to use a time step in your simulation of order 10 to the minus 10 minus 12, which is too small, of course, to perform this simulation in a reasonable time. And so we need to, and also this term is very nonlinear. It's a nonlinear function of temperature and all the other chemical species in the domain. So in order to preserve this coupling and to tackle the nonlinearity of this term in an implicit manner, we resolve it in a fully coupled stiff OD system in each cell. The advantage of this method is that each cell is an independent reactor, so it does not depend on the neighboring cells. And finally, the last ingredient, the last thing that we need in this model is the calculation of the vaporization rate. which is non-trivial for multi-component droplets. While it is quite simple for boiling and also for pure droplets, for multi-component droplets is not so simple because we don't know anything about the interface. We don't know the liquid mass fraction at the interface, the gas phase mass fraction. We don't know the interfacial temperature. Everything in principle is coupled in a nonlinear system of equations. So we developed a proper strategy to decouple this system of equation and to obtain a vaporization rate for the multi-component system. In particular, we assume that the mole fraction of liquid at the interface is equal to the neighboring liquid mole fraction, and the same we do for the interfacial temperature. We calculate the mole fraction in gas phase at the interface using the thermodynamic vapor-liquid equilibrium, and with this information we can compute the total vaporization rate and the vaporization rate for each chemical species. For a reliable calculation of the vaporization rate, it's important to have an accurate method for the interface gradients that we take from the methods for generic solids on Cartesian grids from Johansen and Colella, for example. And finally, once we have the vaporization rate, we can update the interfacial temperature using a root finding strategy, for example. From the enthalpy jump condition, we just computed the vaporization rate, and we obtain the final interface temperature that satisfies this equation. All this thing is implemented in Basilisk, which does not require many introductions in this lab. Essentially, we use Basilisk for two main reasons. It implements a powerful adaptive mesh refinement strategy, and it implements a state-of-the-art methodology for surface tension modeling, which is pivotal for simulation of small droplets and bubbles. It is also very well documented, open source, and all these advantages. Okay, now let me show you some results, starting from the some validation cases where we use incompressible liquid and incompressible gas phases, constant material properties. We tested our model against the benchmark phase change problem, for example, the evaporation of a droplet with a fixed vaporization rate, the Stefan problem, which is the evaporation of a plane, and the Scriven problem, which is the expansion of a bubble in a superheated liquid. These are quite standard phase change problems to test our methods. In all cases, we get convergence, also at second order, so we can move to more complex test cases. For example, the evaporation of a cold normal heptane droplet in a hot nitrogen environment. In this simulation, you can see that the droplet is initially cold and it's heated up by the external environment. As the temperature of the droplet increases, the droplet evaporates, and so the fuel mass fraction in gas phase increases as well until the full consumption of the drop. We repeat this simulation at different levels of refinement, and if you compare the square diameter in time at 3 different levels of refinement, you can see that we tend to converge toward the numerical benchmark results that we use for this validation. In this case, we don't have an analytical solution. If you take a look at the temperature field, you can see that the temperature of the interface is initially cold. It increases due to the external heating until a plateau, a steady state, which is given by the interplay between the heat conduction from the external environment and the cooling due to the evaporation process, which is endothermic. We can also compare our results with the benchmark solution for in the radial profile, different time instance for temperature and mass fractions. You can see that the temperature is continuous across the interface, while we can maintain this sharp discontinuity between the liquid and the gas field and still have a very good agreement with the benchmark solution. Another more complex test case is the evaporation of a binary droplet. I told you that this formulation is multi-component, so let's try it. This is the evaporation of a binary droplet where we have a light and a heavy component. As the simulation starts, the light component evaporates immediately, decreases its mass fraction inside the droplet in the liquid phase, while the heavy component, in response of this decrease of mass fraction, accumulates inside the droplet and then evaporates as well. The third component is an inert species, which is always in gas phase and which is important for combustion simulation. Of course, in this case, we don't have an analytical solution or even a benchmark solution, so we tested the mass conservation of this system for each chemical species. In particular, if we plot the total mass of gas of the two components in time and we compare it with the vaporization rate value, you can see that we have an excellent agreement between vaporization rate and mass of the two species. But in particular, you can see that they are essentially the same as the mass which goes away from the liquid phase. So essentially, we can prove that our method is mass conservative because the amount of liquid lost, the amount of mass lost by the liquid phase is retrieved in the gas phase, right? This is not a very common test in this phase change model, so we can prove that we can actually be mass conservative. Now let's go to more interesting problems, which are droplet evaporation problems with a low Mach formulation, so with variable thermodynamic and transport properties. This is a more realistic situation, and we can actually compare our results with experimental data. We start always from the simulation of cold normalettane in a hot nitrogen environment. The trend is very similar to what you just saw before. We repeat this simulation at different initial temperature and at different ambient pressure. You can see that the trend of temperature on top and species mass fraction on the bottom is perfectly spherically symmetric. We can also see quite well that increasing the ambient pressure, the droplet becomes hotter because we are increasing also the boiling point of the liquid phase. So now let's try to focus on the atmospheric pressure and to compare our results with experimental data. So what we see is that this is the ambient pressure case at different initial temperature. You can see that in any case, at the beginning, you have an initial expansion, a thermal expansion of the liquid droplet that you can capture only with a variable material properties formulation, of course. After this initial stage, every droplet, regardless of the initial temperature, is consumed in a quasi-stationary manner. And of course, as we increase the ambient temperature, the vaporization rate is faster. This is quite expected. Our results are the solid line. The empty markers are a benchmark one-dimensional numerical model, while the full markers are the experimental data. You can see that we have an excellent agreement between our model and the 1D model, and there is just a slight discrepancy with the experimental data that can be attributed, for example, to the missing thermal effect of the solid fiber, missing Marangoni convection, perhaps. But the problem is that if we, small deviation, but if we proceed and we compare other results at higher pressure values, you can see that this gap between our results and experimental data increases a lot, especially at high pressure cases and the low temperature, which are the black line. This effect is less important instead at high temperature cases. So we think that there is something missing in these results, also because this gap has the same functional dependency of the Grashof number, which measures the importance of buoyancy-driven flows in our system. So even if these experimental data aim to be microgravity condition, we try to introduce gravity, in particular residual gravity, and we try to repeat this simulation with the droplet in a gravitational field and see if we can move toward this experimental data. So first of all, we have to hang the droplet on a solid fiber. To do that, we develop an appropriate strategy to locally modify the essentially boundary condition for curvature, and the result is that the droplet bounces on the solid fiber initially, but eventually it reaches a perfectly steady configuration where the pressure gradients, surface tension, and gravitational acceleration are well balanced. Now, if we activate the phase change, you can see that in this case, the trend is no longer spherically symmetric. As the normalettane evaporates, it decreases locally the density field around the interface, therefore introducing buoyancy-driven flows that creates this downward velocity profile that transports the temperature and mass fraction fields. This downward velocity is less important at atmospheric pressure, but as we increase the pressure, you can see that this wake becomes sharper, and we expect it to have a strong effect on the vaporization rate of this droplet. Okay, so if we try again with the atmospheric case and we repeat this simulation at different gravity values, so at 0g, 1 over 100g, 1 over 10g, and g equal to the Hart normal gravity value, you can see that indeed introducing residual gravity, we slowly tend toward the experimental data, both for the cold and for the hot case. Of course, there is not much different at atmospheric pressure, but as we increase the ambient pressure, you can see that, for example, for the 20 atmosphere case, even a small residual gravity can have a strong impact on the vaporization rate of these droplets. So you can see that, and you can see that this effect, as we expected, is more important at low temperature than at high temperature, and also is more important at high pressure cases. So what we proved with this simulation, essentially that these experimental data are strongly affected by residual gravity effect, but this is probably not the only reason why there are this discrepancy between our results and experimental data. Actually, these discrepancies were reported also by many other authors, but this is the only set of experimental data that we have. For sure, there may be other effects, such as Marangoni convection, the thermal effect from the solid fiber, but this is the only one that justifies this functional dependency from the temperature and pressure. Okay, no, it would be nice to study also the interplay between residual gravity and Marangoni, for example. It can be a nice future step. Okay, now let's see some droplet combustion problems. For droplet combustion, we have these two configurations, microgravity condition and normal gravity condition. In both cases, we have to use a L0 value, so a total domain length, which is huge compared to the droplet dimension. So for this case, in microgravity, we use a domain length which is at least 40 times larger than the droplet diameter. And this is important because the flame will expand a lot, and we don't want the boundaries to quench, non-physically quench the flame, okay? So we need to use a very large boundary, and for this simulation, adaptive mesh refinement is pivotal to reduce the computational time as much as possible. In normal gravity, the setup is very similar, but we also suspend the droplet on a solid fiber, as I showed you before, and we refine our domain around the interface of the droplet and around the flame front, which is the red line. An additional trick to limit the computational time is to use just a two-step kinetics. Combustion guy will be a little afraid of these formulations, but this is good to validate the model, reducing the computational time. Of course, we cannot study complex chemical phenomena such as autoignition or soot formation, but it's fine for these simulations. So the first test case is to test the convergence of the model. We have the combustion of a normal heptane in microgravity condition. From the temperature, you can see that the droplet is very small, the white line is the flame front, and the temperature essentially show you the flame profile. The normal heptane, this species here, evaporates, and it's present, of course, on this side of the flame front. It reacts with oxygen, creating CO, water, and nitrogen is the inert for this simulation. So the qualitative behavior is correct. Now let's take a look at the quantitative behavior for different levels of refinement. The black line shows you the square diameter in time. You can see that as we increase the level of refinement, we tend toward the triangles, which are a benchmark one-dimensional models, and also toward the dots, which are experimental data by Hara and Kumagai. We get a very similar slope on the square diameter in time. The blue line instead is the flame diameter. We have a very good agreement with the one-dimensional model, but there is a discrepancy with the experimental flame front. And this happens because actually there is a mismatch in the definition of flame front between numerical simulation and experiments. experimental people will say that the flame front is the peak of luminosity of the flame, while in our case, the flame front is the peak of temperature of the flame. And this is not always the same, especially if we have even light soot formation. So it can be due to the fact that we are using a simplified kinetics and we are using different definition of flame front. Okay, so we can say that we converge toward the experimental data and the numerical benchmark. Let's try to study another test case, which is the combustion of an ethanol droplet, always in microgravity condition, but with a peculiarity, with an initial amount of CO2 in the atmosphere. So in this case, we have 0% CO2 initially present in the atmosphere, 30% and 60% in the last case. We studied different droplets with different initial diameter from 0.36 millimeters to 0.71. You can see from this plot that we have an excellent agreement with experiment, okay, but you can also say, but these slopes are always the same, essentially. But actually, if you plot the dimensionless square diameter in time, you will see that the initial diameter for the 0% CO2 case does not have any effect on the burning rate of this droplet. While as we increase the amount of CO2 in the atmosphere, we see that the larger droplets burn slower compared to the smaller droplet. So to explain this behavior, we try to plot the flame temperature and the flame diameter. The flame diameters are pretty much always the same and do not give us an important information in this case. We can just see that we have the same flame diameter of the benchmark 1D model. While if we take a look at the flame temperature, you will see that at 0% CO2, the initial diameter does not show a big variation in the flame temperature, which are always very close. But as we increase the amount of CO2 in the atmosphere, you can see that we get a strong variation in the flame temperature, which goes from essentially more than 1800 K to 1600 Kelvin. And so this effect can be explained with the effect of radiation, the dissipation due to the radiative heat transfer, because radiation in this system is a direct function of the amount of CO2 in the atmosphere, and larger droplet will take more time to evaporate and will experience this dissipation of heat for longer, and this will result in a lower flame temperature that will also decrease the burning rate of this droplet. But actually, all the test cases that I show you for combustion are things that we can do also with a simple 1D model. So let's try to exploit the multidimensional capability of this model to simulate methanol combustion in normal gravity conditions. At different pressure, you can see that at the beginning there is a spark that ignites the chemical reactions. Once the chemical reactions start, they create a very hot flame which promotes buoyancy-driven flows and a wake that this time goes upward because the density is lower around the droplet. If we observe the behavior as we increase the pressure, we see that again, increasing the pressure, we have higher buoyancy-driven flows and therefore flame which is more stretched toward the vertical direction and which is closer to the droplet along the horizontal direction. And of course, this is expected to influence a lot the vaporization, the burning rate of these droplets. So to check the influence of buoyancy-driven flows in this case, we performed the same simulation for different ambient pressures at microgravity and in normal gravity conditions. And from the black line, which is the square diameter in time, you can see that at atmospheric pressure, we don't have a big deviation between the microgravity model, so the 1D assumption, and this model. It's just a 6% deviation. But as we increase the ambient pressure, especially going up to 20 atmosphere, we can see that the one-dimensional approximation is absolutely no longer valid. We have a 60% deviation from the 1D models. And we also introduce some effects like an initial unsteadiness, which is due to the initial positioning of the flame until reaching a pseudo-steady envelope flame configuration. Of course, we have also a strong effect in the flame front, which will be closer to the droplet, especially as we increase the pressure. And since the flame is closer to the droplet experiences a higher temperature gradients and burn faster. These simulations were performed neglecting water condensation, but water condensation can play an important role in this system because when methanol burns, the interface temperature is lower than the boiling point of water. So essentially, we can have some water which is absorbed back inside the droplet. But we have a multi-component formulation, so we can try to simulate this behavior. And what you can see is that if we don't have water condensation, the droplet is just consumed and follow the d-square law perfectly. If we introduce the possibility of having water condensation, we have a slower burning rate, and then a sudden change in the slope of this curve, which is the extinction point of this droplet. So here, essentially, the combustion is extinguished, okay? And if we introduce some amount of water initially inside the liquid droplet, you can see that the extinction point occur at higher droplet diameter as we expect. Now, for a better comparison with experimental data, we would need more physics in this case. We would need, for sure, the liquid non-ideality, because methanol and water is a non-ideal mixture. We should consider that. And we also need the Marangoni effect, because methanol and water have very different surface tension, and that introduces diffuso capillarity effect, which introduces strong liquid recirculation inside this droplet. Okay, this is all for my presentation. What did I do? Essentially, I extended a volume of fluid model with multi-component phase change, variable material properties, and combustion. Everything you saw is available on the Basilisk, on my Basilisk sandbox, and I hope it's also well documented. We, in some way, advanced the numerical solution strategies for multi-component droplet, multi-component phase change, and we obtain convergence, of course, on the model that we introduce. We also explain discrepancies between prior experimental data and prior numerical simulation, and we measure the error that you have if you use a one-dimensional model for droplet combustion in normal gravity, which is more common than you can expect. And future work, there is a lot of future work to do from different perspectives: numerical methods, additional physical phenomena, and new configuration. For the numerical methods, it would be nice to have a single formulation for managing the velocity jump. Instead of deciding if a double pressure velocity coupling or a pure one-field approach or a Gauss fluid method, it would be very nice to have a single method that works for everything: evaporation, boiling. And additional physical phenomena, I mentioned Marangoni convection, but also the conjugated transfer with the solid fiber is important in some situations, especially when the fiber is large. And it would be nice also to have a automatic transition from diffusion-driven evaporation to the boiling regime. This is quite easy in pure droplets, but it's quite of a challenge in multi-component droplets. And then it would be nice to explore new configurations like interaction among multiple droplets and a full spray combustion simulation. Maybe at some point we will have it. Okay, thanks a lot for your attention. I hope it was not too long.
Before I take questions, I will just say that your sandbox is beautiful. So just go and see Edoardo's sandbox, because it's very nice. Very nice visual things. Okay, are there any questions?
Thanks. I have many questions, but you're in my office, so it's easy to ask. Just one that I have and always had about droplets in microgravity, I mean with zero gravity. Where do the burn gases go? So what's happening? Basically, how is the combustion driven? Because you accumulate burn gases, so where is the oxygen coming from? So what's happening?
Yeah, I think that, well, there should be an initial big chamber with some oxygen in order to keep air condition at the sort of boundaries, and then I don't know, really we should ask the experimentalist for this, but the chamber is usually sufficiently large, I think, that we don't have a strong effect due to I don't know, lack of oxygen, because we consume all the oxygen around the droplet and the chamber is small. They should keep providing, of course, the air for feeding this process. So otherwise, if it was just a closed chamber, we would extinguish the droplet quite easily, right? So, but again, I'm not really an expert of how these experiments are performed. Also because there are many different methods depending on how you create the microgravity conditions. In the results that I show you about the gap in the evaporation, the microgravity conditions were created with a drop tower, which is the least accurate method, but you can also go on the International Space Station, and we actually have many experiments of droplet combustion on the International Space Station. So you can imagine that an astronaut wakes up and that day has to burn a single droplet on the International Space Station. So this is to remark the importance of these kind of studies. Yeah, and that's in that case the residual gravity is extremely low and reliable. I don't know about how they provide exactly the oxygen and the oxidizer.
Thank you for your presentation. I have a question that maybe it's more from your experience. Maybe you can say why, if I understand well, it's very important for you to implement your boundary condition. They are very important in phase change problem. But still you have chosen to deal with one fluid. Well, you know that one fluid, you know, how it's designed, how the one fluid method is designed, and the fact that you have boundary condition that you have to impose at the interface, that's not, it's difficult to deal. So why did you choose to go to volume fluid instead of front tracking, especially in your case, and you are not dealing with phase change topology? So yes, this is just curiosity.
Well, the initial motivation was that we use the volume of fluid because it's most conservative. Then probably there are many new versions of also level set and front tracking that can enforce mass conservation. Why I use a one-field formulation with VOF, and this is a typical approach of all these kind of studies. Essentially, they start from a legacy code. All the legacy code are one-field formulation, and we implement these boundary condition, and then we realize that there are a lot of problems. So yes, probably this is not the best case, but also if you explore the front tracking literature for these topics, you see that there are additional difficulties. In the level set, in the original works on level set, there are never mass conservation tests. Maybe, I mean, we can deal with that, but yeah, for sure there would be many advantages of having a front tracking method. It would be nice to have all the three of them and to be able to switch in a sort of a unified framework, but I had just one PhD for that, so.
So you showed that the influence of gravity, even small remaining gravity, can be important for your droplet combustion. Do you know how it compares with the actual uncertainties? I mean, I guess people have estimated variation of microgravity with microweaves. You know if your range of parameters compares with the uncertainty in the experimental setup?
Yeah, in this case, the 1/10 is definitely in the range that they report. Okay, so yeah, it's quite high in this case. Not really microgravity. they report a range. It's for sure not less than 1/100 G, which is still very high if you consider that microgravity experiments in International Space Station are in the order of 10 to the power of -4, -5, are real microgravity. And I don't know, I should probably ask experimental people to produce new experiments on these configurations, because this is the only set of data, and what people do is to usually use the ones that work in their system.
Was that a drop tower or was it parabolic flight?
It was a drop tower, yeah. But they are this old experiment from 1996 from Nomura. It's the classic set of experiments used by the people, but they typically use just the ones at atmospheric pressure, and then we ignore why they don't work at higher pressure.
Yeah. And do you know how, I don't know, is there a big difference between drop towers and parabolic flight in terms of the quality of micro?
I think parabolic should be more accurate. I don't know the order of...
Okay. Well, I have many other questions. Maybe.
Maybe I missed the very beginning, but I know at one point you discussed, you casually mentioned radiation.
Yeah.
So are you including radiation in your model?
Yeah.
And if so, what's the relative effect of radiation compared to like buoyancy-driven effects?
We have two types of radiation, first of all. We have a radiation at the interface, and also another term which let's say, it's here somewhere, which is the heat dissipation for radiative heat transfer, but it's a very approximated version of radiation modeling, and it's valid only, I use it just for combustion cases, and it's valid only under the optically thin assumption, which means essentially that the flame is thin, and the optical thickness is less than 1. Okay. In this condition, you can assume that the radiation effect is just a heat dissipation. And what you can see here is that including this dissipation, we reduce the flame temperature, especially in these cases at height CO2, because the expression for that radiation is a direct function of the amount of CO2 in the environment. So this is the bulk phase gas radiation. Of course, we are not including the absorption of, because the optical thickness is small, we are not including the absorption of radiation in every point of the domain. It's not so easy to implement good radiation models. And so this simplified version works in these cases. It's fine for these cases. And then we have the radiation on the droplet interface, which is not important in these cases, but it's important when you study, for example, droplet evaporation in a hot environment like this data. These droplet evaporation cases. In this case, you have a hot furnace wall that radiate directly on the gas-liquid interface, and you need to account for that. If you don't consider radiation in this data, even these ones in microgravity, these ones in microgravity, for example, you get a very large discrepancy with the experimental data. So yeah, I didn't mention it because in this experiment it's quite well known that you have to consider radiation from the solid walls to the drop surface.
Thank you.
Yes.